So the trick is basically to approximate the summation by a few samples instead of an exponential number of samples, right? And we'll try to understand with this the help of a simple analogy. I'm sure most of you know this, but I'll still just go over this analogy. So suppose you live in a city which has a population of 10 million and you want to compute the average weight of this population. What will you do? You will go and ask everyone in the population to give their weights to you, most of them. So you can think of X as a random variable which denotes a person, right? So of all the 10 million values that X can take, X can take any one of these 10 million values that you have, 10 million people that you have in your population. Now with every random variable, you also have the weight associated with that. So technically what are you interested in computing? You have X and you have weight of X. I want to compute the average weight of the population. So what's the technical term for that? Expectation. What expectation I need to compute? Expectation of the weight. And this is how you'll compute it. Now what's the number of terms in this summation? 10 million, right? This is all the people in your population, okay? But this is going to be hard. So in practice, what do? We just take some random 10,000 people, compute their weights, and from that we compute the expectation, okay? But while doing that, right, we actually do a lot of stuff which we don't actually realize. So let's see what is it that we actually do. So this is exactly what I'm going to do. I'm going to approximate that expectation by just some 10,000 people from all the people that I have in my population, okay? Now what are the assumptions that I'm making while doing so? Okay, that's fair enough. In fact, what is this formula going to simplify further to? It's going to simplify to this. Everyone agrees with that? So what's the assumption that I've made here? How many of you get that? We make an implicit assumption without actually realizing it. What is the assumption that we have made? All samples from our population are equally likely. In some cases this makes sense, right? So if you look at it as a population point of view, unless like the population is really divided that there are very few people staying in certain areas and most people stay in one area, then there is going to be less likelihood of sampling from this smaller population region, right? But if I just assume that along the city people are equally distributed, then I can just go and pick up random samples. I can just keep walking along the city and just take 10,000 random samples and they are a representative of the population. So in that sense, I can assume that all people in my population are equally likely. Is that fair? Okay. You see a problem with this in many other cases? Can you give me one example where this is a problem? Where you have a space, a universal set, right? What's the universal set here? All people in our population. And everything in this universal set is not uniform. It's not equally likely to get any event from this universal set. What's the event here? Any person that we want to pick. Yeah. Can you give an example from, I'm sure most of you did not hear that, so I'm repeating the question, from something that you have learned recently or from the discussion that we have been having over the past couple of 3-4 lectures. Give me an example of a space in which you do not expect every outcome from that space to be equally likely. Images. Why? Okay, so we'll just go to that, right? So remember that when you're computing these expectations, you make this assumption that all samples are equally likely, which may not be the case. Okay, and we'll see that if that is not the case, what's the right way of doing it. Yeah, but you are able to draw these samples because you are making this assumption that every sample is equally likely, right? I'll just continue with this discussion and then I'll give you an example where this is what I want to say. Maybe I'm not saying it correctly, but it should become clear, right? So this looks easy, right? Why can't we do it for our task? Our task was also that we had these all possible values of v comma h, just as we had all 10 million possibilities for the people, just as we sampled any 10k from there. Why can't we approximate this all possible values of v comma h by any 10k values of v comma h or any reasonable values, right? Let's make it 1 million for that matter. Why can't we do that? That's exactly the analogy. You have 10 million samples in your space. You just approximate it by a small number of samples. You have 2 raised to m plus n possible values. Just draw a reasonable number of values from there, say 1 million or 2 million, and just approximate the summation by that. Okay? That looks easy, right? That is what we should do. This is what I'm trying to tell you, right? Instead of all these 2 raised to m plus n values, just consider some samples, and let's be vague about the number of samples. Let's be generous, right? We'll assume 1 million samples because 2 raised to m plus n is a really large space. So even if you draw 1 million, it's going to be a very small number of samples from that space. Okay. Okay. Why is this not straightforward? And for simplicity, what we'll do is we'll just focus on the visible variables, right? So let's assume that we are only interested in summation over all v's. We don't have a term which has a summation over v comma h. So we just have 2 raised to m terms and not 2 raised to m plus n terms. This is just for the sake of simplicity. And even with that, we can really see that it is slightly hard to do that. So what does it mean to draw samples from P of v? We know that vi's belong to 0, 1 and every v vector belongs to 2 raised to m. Now suppose I decide that I want to approximate this sum by 10k values. Right? Can you construct these 10k values? Just as in the case of the population, you just took 10k people, right? Because they were just there and you just took them. In the case of this, in the case of visible variables, if I ask you to give me 10k samples, can you give that 10k samples to me? How will you come up with these 10k samples? How will you come up? If I ask you to give me one valid configuration of V, give me an answer. All zeros, all ones, some zeros, some ones. So it's not very easy, very difficult to construct samples from this space, right? You just need to decide, I'll set some values to 1, some values to 0, and all these things which I've written here are valid samples from this space. I can just construct any of these samples. It's not very hard to construct these 10k samples. So I'll just take these 10k samples and then approximate the sum using this 10k samples. What's wrong with this? What are we again assuming here? All samples are equally likely, right? That's why I'm saying that I'll just have this large space, I'll just pick one from here, one from there, everything, right? Everything is uniformly possible. Actually, if you are considering images, okay, and let's assume there are no blank images that you ever see. Should I have actually drawn this sample? No. This was a sample which has 0 probability, and I've actually drawn it. That's the problem, right? As compared to the population example, that's the problem that we have, that all samples in this space are not equally likely. So when we are constructing these 10k samples, which 10k from the possible 2 raised to m plus n should we consider? That's the question that we need to answer. Is that clear? Is everyone fine with that? Okay. Now that's where the catch is. Unlike our population analogy, all these are not equally likely. Why? Because if you consider the case of images, the top image is more likely to be seen. The bottom image is not likely to be seen. Right? If you are looking at images of natural scenes or or even animals or whatever, the bottom image is definitely not likely. And my space is so high dimensional that of that entire space, actually there are very, very few samples which are legitimate. All the other samples are noise. Now if I'm going to draw everything uniformly, I'm going to get a lot of these noisy samples which do not actually belong to my distribution. I'll just not be able to get only those images which are skies or birds or whatever. All of you get this? That 2 raised to m plus n is a very, very, very high dimensional space. It has many, many, many points, of which only a very, very, very few points are the points that we are interested in. And while computing this expectation, we need to focus on those points because all the other points have a 0 probability. Does that make sense? Okay. So this is the difference, right? So earlier you had this uniform distribution, but now you have some kind of a multimodal distribution or just a skewed distribution, where only some regions have high density samples and everything else is not likely, right? There is nothing likely from this region which I have just painted in our distribution. So if I draw samples from there, I can actually tell you what this point is, right? This is some in this, if I think of this as a square grid, then this is some 3, 1 or some point, right? I can tell you what this point is. So I can always sample this point. But when I sample this point, I'm doing something which is wrong because this is not a good sample. Okay? Okay. So we need to draw samples from the high probability region and fewer samples from the lower probability region. So whatever sample we draw should be proportional to the probability. This was not a problem earlier because everything was equally likely. Okay? So that is where the problem lies. Now if I want to pick up a sample according to its probability, what do I need to compute first? The probability. Can I compute the probability? To compute the probability, what do I need to do? what's the term that I'll divide with? Z. And Z by itself is untractable because again I have an exponential number of terms in it, right? So I have this dilemma, right? I want to draw samples according to a probability distribution, but I cannot actually compute the probability distribution because computing the probability of any sample itself is exponentially complex. Is that fine? So you see the problem here? So to draw these samples, we need to compute P of E comma H, and also to compute the expectation, which is saying the same thing, we need to know the probability of V comma H, right? Because you have this in the expectation. And this is hard to do because you have the partition function. And the partition function has an exponential number of terms, okay? So hence, unlike our population case, right, approximating this sum by a fewer samples is not straightforward because we don't know how to draw these fewer samples. To draw these samples, we again go back in circles and we realize that we again need to compute the probability. Okay, so just go back and think about this, and this is what the conclusion is, right? I get it that drawing samples from the distribution P is hard. What's the distribution P? P of E comma H. I cannot draw samples from this distribution. So the question that we are going to ask and try to answer in the next lecture or over a few lectures is that, is it possible to draw samples from another distribution, Q, which is an quote unquote easy distribution, as long as I am sure that if I am drawing samples from this distribution, they are almost as if they came from my original distribution. A very convoluted question, but do you get the motivation for that? P is a hard distribution. I cannot compute P because I need Z, which is intractable. What my proposal is, what if I give you a distribution Q, which does not have this hardness in computational terms? I can easily compute that. And I can give you some guarantee that P and Q are very similar. That means if I'm drawing samples from Q, if I'm drawing visible variables from Q, if I'm drawing the vector V from Q, if I can give you an argument that those V's are actually very similar to what I could have gotten from P, okay, then it's okay to use Q. Does that make sense? Because Q is easier to use. Q is easier to deal with. So that's what we are going to do in the next lecture when we talk about Gibbs sampling. That's the overall idea, that if you have a P and if you have a Q, such that P is very hard to draw from, but Q is very easy to draw from, can you set up a Q which has two requirements? One is it's easy, and the other is that samples from Q, after a while, start looking very similar to samples from P. That's the motivation behind Gibbs sampling, and that's what we're going to do in the next lecture. Okay? So go back and revise today's discussion. In particular, be very comfortable with the idea of why we need to do sampling and why it is not straightforward in the case of RBMs. Okay? And not just RBMs, actually what you have seen is applicable to all graphical models which have these exponential of number of terms, because all the graphical models will have this partition function which you will have to normalize over or marginalize over, and whenever that is hard to do, you have to resort to some kind of sampling methods, right? And that's what we'll do in the next lecture. Okay, thank you.